えーっと、Okay, so this is number 106. We start from this part, deformation gradient vectors. We know that an element dx gets mapped into dx during deformation. Okay. So in this deformation, the time is discrete. Okay, here, this is time is 0, and this is at time, some certain time. It's not a continuous deformation. This is like a deformation between t equals 0 and t equals t1. Okay, here what we are considering is this is a time, and there is a 0, and there is some time t1. So you are comparing the state of material between this here and here. Yeah, we don't consider like a continuous deformation. Then dx can be expanded like this, and g1 is like this. G1. Okay. I think it's okay. This just means dx. Okay, okay. Originally we have this. So then this is d4. So how do you consider this? dx, dx. This is like partial 1 partial x1 e1 dx1 plus partial x2 partial x1 e2 dx1 plus partial x3 partial x1 e3 dx1, something like this. So then there is an implication. Okay. Here you have index 1. So this partial 1 implies partial large x1, I think. here too, you have one, no, okay. Here, like this one imply the index for capital X. So this one is an index for capital X. So this one is also an index for capital X. So this partial one actually means partial x1, large x1. So what is this? Sorry, gx g1 dx1 deformation gradient vector g1 and g2. If we had marked E1 in the undeformed configuration, we would see its image G1 in the deformed configuration. The three unit vectors have as their image. Yeah. Three unit vectors have G alpha as their images. These are known as a green deformation gradient vector. Figure 5.3. This is figure 5.3. It's called green deformation vectors. Green deformation gradient vectors. Similarly, the unit vectors EI in the current configuration had their images GI. Is it similar? Similarly, okay. In the undeformed configuration, these are called Cauchy or Cauchy deformation gradient vectors. These two systems of vectors are intimately related to the base vectors we had seen in chapter 3. To see this, consider an arbitrary element dx getting mapped into dx. We have dx partial alpha x dx alpha g alpha d partial I think it's okay. Same thing, right? I think it's same thing as this. What is difference? dx. It's confusing. So we take this guy. Let's see. So what's the difference? dx. Now we have summation. Yeah, I think so. We just changed. See, here is one. We were considering only a first component, but here we have alpha, and this is summation implied. I, summation is implied, implicit. The length of these elements can be expressed as ds square is d alpha, dx alpha, ds square is dxi. If we write the current length in terms of material coordinates, we have ds square is partial x partial alpha x d x alpha dotted with partial beta x d x beta, which is g alpha dotted with g beta d alpha dx alpha dx beta, and that is called g alpha beta dx alpha dx beta, where g alpha beta is our old metric tensor. Oh my god, this is called our old metric tensor, which is the dot product of the base vectors. Dot product of base vectors. In continuum mechanics, we refer to G as green deformation tensor. Green deformation tensor. A parallel consideration in terms of spatial coordinates gives ds big S square is g ij dxi dxj gij equals gi dot gj. The tensor G is called Cauchy deformation tensor. We may express the deformation tensors large G and small g as G equal FF transpose, G equal FF transpose. The tensor G and large G and small g are symmetric by virtue of their definition in terms of dot product, because the squares of distance are positive. These tensors matrices are positive definite. It's so hard. What was the F? F is this way, so then G. Maybe I move ahead. Okay. Curvilinear systems, base vectors G alpha or Gi remind us of curvilinear coordinate systems. If we had etched a rectilinear grid on the undeformed body after deformation, we would see the grid deformed into a curvilinear net. This is the curvilinear system associated with base vector G alpha and matrix tensor G. The context of general tensors, it is appropriate to use x alpha up and xi up as the coordinates We can imagine a similar picture for a rectangular grid in the current configuration. We may introduce reciprocal base vectors G alpha up and G up, up mm, I up to go with the curvilinear coordinates. These are defined as like this. Using reciprocity of f and f, we see that G alpha G beta is delta alpha beta G I G J delta Ij. Associated with the reciprocal base vectors are the reciprocal deformation tensors G alpha beta and Gij, which are inverses of G alpha beta and Gij respectively in matrix form. Matrix form G inverse is something like this, G is something like this, small g inverse is something like this, G like this. The reciprocal deformation tensor G alpha beta and Gij are attributed to Piola and Finger respectively. The characteristics of a deformed body in the neighborhood of a point X can be described as something like this. In classical continuum mechanics, it is postulated that the neighborhood can be as small as possible. Then the second order quantities dx alpha dx beta render the third term negligible. As a result, the deformation gradients partial alpha xi completely define the characteristics of the deformation. Materials satisfying this postulate are called simple materials. To make into account the coarse in microstructure of certain materials, we are not permitted to assume that the third term is negligible, and we may have to include the second derivative in the theories. Strain tensors. The lengths of elements before and after deformation are given by something like this. Strain tensor E alpha beta and Eij are measures of the change in length. The strain tensor E is called the green strain and small e is called the Allemande strain. The names Lagrange strain and Cauchy strain are also used respectively for these two quantities. It is easy to see that both of these strains are symmetric tensors. A relation between these two strain measures can be established as something like this, which have the matrix form E equal F transpose. Large E is FEF transpose. By use of something xi is something like this, x alpha is something like this, the deformation gradients became something like this, the deformation tensors became something like this and this. Now the strain tensor can be written as like this in engineering notation using U, V, and W to represent U alpha and X, Y, Z to represent X alpha. We have EXX, EYY, EZZ, EXY, EYZ, EZX. Similarly, the Almazy strain components can be written as EXX, EYY, EZZ, EXY, EYZ, something like this, okay? So very complicated. 5.3.1 Decomposition of displacement gradient. Displacement gradient, partial I uj and partial alpha u beta, can be resolved into symmetric and skew-symmetric tensors. Let something like this, where E ij and E alpha beta are symmetric tensors called infinitesimal strains, and Rij and R alpha beta are skew-symmetric tensors called infinitesimal rotations. Skew-symmetric tensors called infinitesimal rotations. These can be written as this. The Almancy strain components are related to the infinitesimal strains in the form something like this. When Eij and Rij are small, the Almancy strain is approximately equal to the infinitesimal strain further as neglecting higher order term. In other words, when the displacement gradient and rotation are small, the material description and spatial description are identical. Stretch. Consider element dx deforming into dx. Let us attach unit vectors n to dx and n to dx. Then the ratio ds over ds is called stretch. The ratio depends on the orientation of the element. We have lambda n and lambda n. What's the difference? For the stretches in the material and spatial descriptions. I think this is same thing, right? Is this the same thing, same quantity? Should it be equal? I'm not so sure. This should be equal, right? I think. For the stretches and the materials and the spatial descriptions. As special cases, if n equal n1, we get something like this. And if a small n is E1, we get something like this. Note that blah blah blah. A similar rotational strain rotation. Oh my god. Deformation ellipsoid. polar decomposition of the deformation gradient. Stretch and rotation. Polar decomposition. Strain tensors. Example, square root of matrix. Logarithmic strain. Change of volume. Change of area. Change of area. Compatibility equation. I think we should go up to 5.6. What else do we have? Then we should go to motion. Right? Okay, let me see. I have to study more by myself. So let me think about it.